Good morning to all of you. Today I'm going to present about the electropolicing for the subject advanced metrology. So these are my contents. Now coming to the first part, that is what is introduction to the electropolicing. So what is electropolicing? Basically, electropolicing is a metal finishing process. It removes thin layer of material from a metal surface, resulting in a smooth, bright, and clean finish. Reverse plating. It is the process of reverse plating because metal ions are dissolved into an electrolyte bath. Now, key objective of electropolicing. The key objectives are surface smoothing, brightening, and corrosion resistance. What is surface smoothing? It removes microscopic peaks and valleys on the metal surface, reducing surface roughness. Brightening enhances the natural shine of metals, giving them a reflective and aesthetic appearance. Corrosion resistance removes impurities and creates a passive oxide layer, significantly increasing the metal's resistance to corrosion. Now, the electropolishing process of earth, we can also see in the figure. How electropolishing works. These are the steps 1, 2, 3, and 4. Step 1, the metal part is immersed in an electrolyte bath containing a specially formulated acid solution. Step 2, the metal acts as the anode in the electrochemical cell. Step 3, a direct current is applied across the metal and a cathode in the bath. Step 4, the current causes the surface metal to ionize and dissolve into the electrolyte solution, selectively removing microscopic peaks faster than value. Now, key components of the process. This includes electrolyte solution, direct current, and metal as anode. Electrolyte solution is usually an acidic mixture, often containing sulfuric acid or phosphoric acid, sometimes also oxalic acid. Direct current provides the energy needed to drive the electrochemical reaction, typically in the range of 5 to 40 volt. Metal as an anode. The workpiece to be polished serves as the anode, whereas surface metal is dissolved uniformly. Mechanism of electropolishing, we can see in the figure. So, anodic dissolution mechanism. Electropolishing works through anodic dissolution, where metal ions are removed from the workpiece surface. When the metal is the anode in the electrolyte cell, the direct current causes metal atoms lose electrons and form metal ions, which then dissolve into the electrolyte. The process is controlled by the current density. There may be two possibilities: high current density and low current. High current density, at the high current density, the peaks of the surface leads to faster removal of material, while in the lower current density, valleys results in less material removal. Surface asperity removal. Electropolishing preferentially removes microscopic peaks on the metal surface. This selective removal smooths the surface, reducing the roughness and producing a bright, reflective finish. The process also leaves behind a passive oxide layer, enhancing the metal's corrosion resistance. Results after this mechanism, a smoother, cleaner, and brighter metal surface with improved physical and chemical properties. Now, the materials for electropolishing. However, many materials can be used for the electropolishing as per the requirement. You can also see in the figure. But generally used are stainless steel, aluminum, copper, nickel, while sometimes titanium, brass, and some alloys also used for the electropolishing. Now, importance of metal choice. The efficiency of electropolishing is highly dependent on the metal's properties, such as its chemical composition and surface characteristics. A stainless steel responds exceptionally well to electropolishing due to its chromium content, which forms a passive oxide layer, enhancing corrosion resistance. Aluminum requires a specific electrolyte solutions and process conditions for optimal results due to its high reactivity. Choosing the right metal ensures optimal surface finish, corrosion resistance, and aesthetic quality, making the process more efficient and effective. Now, the parameters affecting electropolisis. Key parameters are electrolyte composition, current density, temperature, and processing time. Current density determines the rate of metal removal. High current density, in the case of high current density, faster material removal, but can lead to rough surface and heating. While in the low current density, slower but more controlled process, producing a smoother finish. In this, we need to choose optimal current density that must be maintained for a uniform and a defect-free surface. Now, the temperature. High air temperature generally increases the rate of metal dissolution. However, too high a temperature can lead to excessive gas formation, uneven surfaces, and electrolyte breakdown. Temperature control is key to maintaining process stability and achieving a consistent surface finish. Process time. Longer processing time results in more material removal, enhancing a smoothness and brightening. Excessive time can lead to over-polishing, potentially damaging the metal surface. Finding the right balance is crucial for achieving the desired finish without compromising surface integrity. So, depending upon our requirement and the thickness and the characteristics of the material, we can choose the appropriate processing time. Influence of surface finish. Proper adjustment of these parameters results in an optimal surface with reduced roughness, high reflectivity, and improved corrosion resistance. Incorrect setting can cause defects like pitting, rough surface, or inconsistent brightness. Now, coming to the advantages of electropolishing, these are the advantages. Improved corrosion resistance, enhanced aesthetic, reduced bacterial adhesion. If we are comparing the electropolishing with respect to the mechanical polishing, so in this comparison, we can see while in electropolishing achieves a higher degree of smoothness and uniformity, can access complex geometries and internal surfaces, removes surface impurity at the microscopic level. While in mechanical policies relies on abrasive and physical force, which may introduce micro scratches, can be time consuming and less effective for intricate shape, may not achieve the same level of corrosion resistance as electropolishing. Now we are coming to the applications of electropolishing. So these are the few applications, while not limited, it can be many more. So like medical devices, food processing equipment, aerospace component, electronics. In the case of medical devices used for surgical instruments, implants, and medical equipment, provides a smooth, clean, and corrosion resistant surface, reducing the risk of bacterial growth and contamination. Food processing equipment. Electropolishing polished surfaces are easy to clean and sanitize, making them ideal for food and beverage process machinery. Reduces the risk of food contamination and ensures compliance and with health standards. Aerospace components. Applied to components like fuel tanks, pipes, and brackets to reduce surface roughness and improve corrosion resistance, enhance the fatigue life and performance of critical aerospace parts. In the case of electronics, used for manufacturing semiconductor components, connectors, and other electronic parts. Creates a smooth surface that ensures optimal electrical conductivity and reliability. Now we are coming to the what is the my experience related to the electropolishing. In my master degree, I worked for my thesis, my master thesis, that is a anodic aluminum oxide nanomembrane fabrication for the hemodialysis process of the kidney patient. In that, I have used an aluminum metal for the electropolishing. So see, these are the right picture. That is the outside view of the electropolishing system. In this, we have made a homemade. This is basically a homemade system, not the industrial system, in which we have made a fridge, a small fridge. Inside that, there is a glass jar, and here there are two lead cathode, and here is the uh, here is the metal connected as the anode. Here is also a temperature, thermometer for the temperature. So in this case, and here is the schematic diagram. You can see this is the opening for the fumes hood. So some gases produced during the process can go out. This is the insulating cap. This is the glass jar. This is the lead cathode, aluminum sheet. Instead of aluminum, anything can be taken for the for the electropolishing. This is a thermometer to measure the temperature. We kept the temperature generally between 0 to 4 degrees Celsius. Here the solution using 0.3 m of gelic acid, heat exchange coil, magnetic stirrer. This is the very important, the magnetic stirrer, because one inside the system and another in the solutions. They wrote in the opposite direction to keep the solutions as the informed solutions. So now, thank you for your kind attention.